Hey everyone, welcome. So in this video, I want to walk through a couple of the derivations in the geometric series. Now, it starts off as a mathematical formula, but it is the major concept of time value money. And it has been used in a couple of the basic financial mathematical classes, such as present value of annuity, that sort of thing. So in this video, we're going to talk about mathematical background, a couple of derivations to show you guys the back end, how this thing works. Let's say I could have a number 2. That's going to be my first number. I could also have number 4, number 8, number 16, so on and so forth. And now the question is, what is the sum? The most basic way is just to add them together. So you do 2 plus 4 plus 8 plus 16. And let's say those are the only 4 numbers that you have. Then you're going to have 6 plus 24, which gives you 30. So for 4 numbers, this sounds easy, but what if this number is a lot? What if it's 10 numbers, 20 numbers? What if it's n numbers where n is a large number? This kind of math becomes very laborious, and we don't like that. So then the idea is, okay, why don't we come up with some sort of fancy formula such that we can summarize this and just plug our numbers into the formula and then be done with it. So the key idea here is to realize that the number 2, which is the first digit in the series, is essentially 2 to the power of 1, and that basically gives you 2 itself. And then you look at number 4, which is the second number in the series. It is 2 to the power of 2, and that becomes 4. So on and so forth. You look at the third digit, number 8, and that is 2 to the power of 3, and that gives you number 8. Now, notice that 4 is nothing but the previous number times 2, whereas 8 is also the previous number times 2. So in other words, as you continue the series, all you gotta do is multiply by 2, and you have yourself the next digit. So when you discover a list of numbers following this kind of convention, you have yourself a geometric series. And then you denote these multiplier as R. Then the formula is saying Sn equal to A1, 1 subtract R to the power of n times over 1 subtract R, whereas n is the total number in the series. So this is the formula that we're interested in deriving. And today we're going to talk about where that formulas come from. Let's say you have A1 to be the first number, and then you have A2, whereas A2 equal to A1 times the multiplier R. And then you have A3, which equal to A1 times the multiplier R 2 times. And then so on and so forth until you have AN. Given a series like this, the sum is written as A1 plus A1R plus A1R squared plus ... plus AN, which is A1 times R n minus 1. Now, people might get confused, why does n minus 1? This is n minus 1 because we have total of n numbers. And then we're counting the first guy, A1, technically speaking, as a first number. But this R here in the second term has actually a power of 1, whereas in the first term, there's no R, which you can think of as A1 times R to the power of 0, because this R to the power 0, it just comes down to 1, which then gives you A1 itself for the first term. Since you are counting from 0, which is the first term, that is why here the power to the last term is n minus 1. So from here, what we want to do is we want to manipulate this formula just a little bit so that we can reduce it or somehow simplify it. Now, the way we do that is we multiply left-hand side and right-hand side by a factor of R. So what we're going to do is multiply left-hand side and right-hand side with a factor of R. So to make our lives easier, let me denote this as our formula 1 on the right-hand side of the formula. And then the next thing I'm going to write is going to be formula 2. So left-hand side multiplied by r. What is that? That is r times Sn equal to, now we're here at the right-hand side. Let's multiply everything by an r. So r times a1 plus a1r. Here I can just copy from above, a1r squared, and so on and so forth, all the way to a1r n minus 1. Okay, so that is our formula number 2. So here's a caveat. I want to take the first formula and subtract the second formula. And the reason I want to do that is because some terms in the middle, they get canceled out. So what I mean by that is this. This r here in the beginning of the right-hand side of the equation, we can distribute this into the parentheses. So what that's going to give us is a1r plus a1r squared plus a1r to the power 3 plus dot 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 plus a1 to the power of r, a1r power of n. Now notice carefully that the minute I do that, these a1r term, that's a second term from equation 1, is actually same as this a1r, that is the first term from the second equation. And we can keep observing the similar pattern, a1r squared, that's there in the first equation, is exactly the same as a1r squared there in the second equation. So we want to get rid of that, and the way we get rid of that is we take the first equation, subtract the second. So what we're going to do is we take equation number 1, subtract equation number 2. Okay, let's see what that gives us. So on the left-hand side, we have Sn subtract Rsn. So let's write that out. We have Sn subtract Rsn equal to, on the right-hand side, notice that some of these terms are going to disappear. So a1, unfortunately, nothing's matching that. So a1 comes down here. Let's write that down. Now the second term of equation 1, a1r, that cancels off with the first term of second equation, a1r. So that's gone. So we don't have to write anything down because there's no impact to the result. And the third term is a1r squared. That cancels out with this a1r squared here in the second term of the second equation. So that cancels out. Now you guys get the idea, right? So these dot 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 in the middle, they all get canceled out until this last term, that get canceled out. But the last term of the second equation, this a1r to the power of n, nothing is canceling that out. So this becomes subtract a1r to the power of n. So this formula I could work with. Then that is a much easier formula. So what we have here is just do a little bit of algebra. On the left-hand side, we have Sn times 1 minus r, because we want to distribute this Sn out of these two terms. And we continue from there, equal to a1 subtract a1r to the power of n. So let's factor a1 out. 1 minus r to the power of n. And then we're left with Sn on the left-hand side, and we want left-hand side to just be Sn. So that's why we want to move this 1 minus r to the right-hand side. And the way you do that is you divide it by 1 minus r. So this is going to give you a1, 1 minus r to the power of n, and this is over 1 minus r. And there you go. That is the final formula. So from here, we haven't finished yet, because here we're assuming that this is n terms, right? Whatever that n is. If you're looking at bond, if you're looking at coupons, if you're looking at present values, if you're taking a mortgage, you have a limit to n. The n can be infinity, right? 10 years coupon, 20-year mortgage, 30-year mortgage. You know, n is always a fixed integer, positive integer. But what if n can go to infinity, right? What if you have an annuity that's just gonna keep coming? Like, what if something like a dividend, right? So then we're talking about this n to be a very, very large number that can potentially go to infinity. So in other words, what's really going on there is we want to have discussion that n can go to infinity. So then what's going to happen then? Let's look at the following scenario. Let's say you have some sort of r, arbitrary r, such that the magnitude of that number is less than 1. If that is the case, and you allow n to go to infinity, then what's going to happen? So to figure this out, let's look at the simple equation. We can just pick a arbitrary number, right? Let's pick r to be 0.9. How about that? It is a number less than 1, so that satisfies the premise. Then what's going to happen is you can take a look at the following algebra, right? R to the power of 1 is 0.9 to the power of 1, which is the number itself. From there, you can check out the second power, right? R squared, and that gives you 0.9 squared, which is 0.81, all right? And then you can take a look at the power of 3, right? So R3, that is 0.9 to the power of 3, and then you can just take 0.81 multiply 0.9, which is going to give you 972, 0.729. So now you guys get the idea, right? As this number goes up, right? R4, R5, R6, I may not know the value on top of my head, but what I do know is this number keeps getting smaller, right? 0.9 is going to be bigger than 0.81. 0.81 is going to be bigger than 0.729, and then so on and so forth. This number keeps getting smaller. So you can take a leap of faith such that when this power term 5, 6, 7 gets bigger and bigger and bigger, this number is getting closer and closer to the value 0. It's not going to reach it, but it will be very close to it. And that is the idea of limit. So how do I write that down rigorously? We use LIM as limit notation, and then we say n goes to infinity. And then we simply say, hey, that's the condition. Now what's the formula? The formula is r to the power of n. And what's the answer to that? Well, the answer to that is essentially 0. So that is an interesting mathematical phenomenon that we're going to take advantage of. Okay, so why do I mention this? The reason I want to mention this phenomenon is because if you look at the equation that we derived above carefully, you notice that this r to the power of n is actually in the formula. Now that's interesting. Why don't we take a look at that down here? So let's recall our formula of the sum of a geometric series Sn that equal to A1, 1 subtract Rn, and this is over 1 subtract R. Now, if I want to take a limit of this geometric sum, and then I let n go to infinity, and again, why do I want to do that? Because I'm assuming this cash inflow is annuity, and n can go on forever. So if I'm making that assumption, I'm essentially writing this limit. I'm giving that limit command to this equation. And the consequence of that is this Rn is here, and that is the only term in the right-hand side of the equation that gets affected by the limit, because limit only says something about n. It does not say anything about A1 or R or any other value. This is the only number that's going to get affected by the limit, which happens to give you 0. So knowing that, let's write that down. So the right-hand side of the equation now becomes A1, 1 minus 0 over 1 minus R. And of course, 1 minus 0 doesn't affect anything. So this becomes A1 over 1 minus R. And there you go. That is the sum of geometric series if n goes to infinity. Now, that's not it, right? Because in the financial mathematics, we actually have a slightly different formula. It certainly doesn't quite look like that, right? And as a matter of fact, let's write that down here. You might actually be looking at this kind of formula. So you might see something like this. Present value at time t equal to cash flow at time t plus 1. And then you have like 1 minus r, subtract 1 minus r. And you have 1 over r, subtract 1 over r. Here, then you have divided over 1 plus r to the power of n, close parenthesis. So you might see something like this. Well, this is essentially derived from the left-hand side, the sum of geometric series. So let's check out this, right? Let's see how this can be derived. The first thing you want to notice is the formula from finance is actually a discount. It's not a multiplier. So before, the setup that we have is A1, A2, whereas A2 equal to A1 times R. And then we have A3, where A3 equals to A1 times R squared, that sort of thing, all the way to AN. Now, this is the multiplier, right? So let's write that down. This is a multiplier. In finance, we are under a different kind of setup. So now, this is the finance. So let's say parenthesis finance. The setup is A1. That's a first cash flow, so nothing happens there. But the second term is a little bit different. A2 is not A1 times R. What you really want to do is discount A2 back. So the present value of that is really A2 over 1 plus R. And then you can use the same philosophy and look at the next number, A3, and if you discount that back, the present value is A plus R to a square. So this is the kind of the relationship that we're talking about. So this is not a multiplier. You're actually trying to discount this. So then what's really going to happen is we need to do a change of variables. We need to let A to be x1 plus I to the power of minus 1, and R to be 1 plus I to the minus 1, right? Because now this A, you want to discount this x back. That's why this is a minus 1. And then this factor R is not a multiplier. It's a discount factor, right? Because this power here is a minus 1. So we need to make this change of variable as well. Now, after we make these two change of variables, we can put all of these back in the formula, and then let's try to simplify it. So what is the formula that we derive above? The sum of geometric series, Sn equals to A 1 minus Rn over 1 minus R. What we're going to do is we're going to multiply minus 1 on top, and then we're going to multiply minus 1 in the bottom. Basically, we're going to multiply this thing that's minus 1 over minus 1, which does not change the formula. So let's try that. A, now it becomes Rn minus 1 over R minus 1, because the order changes because of the minus sign. Now, that's not just it. We haven't done anything to this A yet, right? Because we changed the variable for A. So let's do that. Let's get rid of this A, and then let's replace it with the change of variable. So this becomes x1 plus I minus 1. Now, after I've done that, notice that here I still have this R in the middle that have not changed to the variables that we want yet. So let me rewrite this formula by changing R to 1 plus I minus 1. So that becomes x1 plus I minus 1. And then here, this ratio, let's start from top. The top of the fraction is 1 plus I. Here we have a minus 1, but notice that this is to the power of n, right? So that becomes minus n. And then you have minus 1, that stays the same. And then that's the top of the fraction. Divided over the bottom of the fraction also need to be changed. And that's a relatively easier job because it's just R minus 1. So let's write that down. 1 plus I to the minus 1 minus 1. Now, to make our lives easier, let's do a small algebraic trick. Let's multiply 1 plus I over 1 plus I. And obviously, top and bottom are the same, so that I'm allowed to do this option without changing the result of this equation. Great, let's do that. So this equal to, now here's when things get a little bit interesting, right? So you notice that here we have so here we have 1 plus I to the power of minus 1. Here we have 1 plus I. It practically cancels out. I like that. I like when things cancels out. So let's scratch that off. Let's scratch that off. That makes our life easier. And we're almost there. So here you have what? X. We have left us with 1 plus I to the power of minus n, subtract 1. And then here we have over 1 plus I to the power of minus 1, subtract 1. And then notice that here we have this one more term here, that's 1 plus I, then we need to get in here, right? So let's do a small draft on the right-hand side. What will happen if you get that in there? So here's our draft. We say 1 plus I minus 1 times 1 plus I minus 1 plus I. Because you are taking this 1 plus I as a factor, and then you are multiplying in both of those two terms. And that gives you this thing that was written in the draft section. Now, of course, left-hand side happens to equal to 1. So that makes our life easier. That's why we do that. Here, you're left with x, 1 plus I to the power of minus n, subtract I, and the bottom of this becomes 1 minus 1 plus I, which of course you can simplify it, right? Because this 1 and 1 cancels out. So let me get rid of that. So let me rewrite it. So you have minus I. So now here, since you have this minus I, we don't like that. Let's get rid of that minus. And the way you get rid of that minus is you multiply minus 1 over minus 1 to get rid of this minus sign. So what's the result from there is we're left with 1 minus 1 plus I to the power of n over positive I. And that gives us x times 1 over I subtract 1 over I divided by 1 plus I to the power of n. And oh, I missed the minus sign here. And let's add a parenthesis. And there we go. That is the SN if you have cash flow discounted back from the future to the present. Let's write that down as a box. And that is the financial formula that we all use to compute the present value of a stream of cash flow, with I as your interest, X as your payment, and N to be the total number of payment. There you go. Hope you guys enjoyed this video, and I'll see you guys in the next one.